Our next speaker is Tomer Weiss from the Technion. Tomer Weiss is a PhD student in computer science at the Technion, supervised by Professor Alex Bronstein. He focused on using deep learning for inverse design in computational imaging, and Tomer earned his master's degree with the honors in computer science from the Technion, and his bachelor mathematics and computer science from Ben-Gurion University. Tomer will talk about computational imaging.
Thank you. Yes. So, small update. I already finished my PhD. This is outdated because of the conference. Yeah. Okay. So, I'm going to present you today some of my PhD work on computational imaging and also on chemistry and molecular design. And it's related. You need to believe me, but you will show it soon. So let's start. So I guess all of us know that neural networks are great, right? They can do many great things. Let's only envision. We can do many things that we couldn't do before. But the question is, when I started my PhD, I didn't want to improve one of this area. I want to think about some new things, what else we can do that nobody did before. And soon we will see what we did. So the general ways that we are using neural networks, right? We have input, we throw it into the model, we get an output, we calculate a loss, and then we use the gradient of the loss to optimize our model, to change the parameters in order to get the best performance. But the questions that we asked, and people before us also in computational imaging, maybe we can use the gradients and backpop them even further to change the input. What does it mean to change the input? Maybe to change the way we create the input. And if we look on imaging, so Y is like the object of interest, X is our measurement. So we have some forward models, the camera, or the MRI machine, or CT, or any imaging device. And it has some controllable parameters, but we will get eventually X, the measurements. And then we have the neural networks that try to reconstruct the original object Y. And we suggest that if we will try to optimize both the forward models, the acquisition parameters of the imaging device, and the neural network, we will get better performances. We will get better data, so it will be easier to reconstruct better and get better end performance. So I will show you some examples that mainly in MRI, but also in MIMO radar imaging, and even in molecular design, like I promised. So in MRI, we all know it's a great machine. It can do many things, but unfortunately, it's slow. You need to lie for a long time inside the machine. It's uncomfortable. It's costly. It's very inefficient. So people thought about way how to expedite the time you lie in the machine. One of the ideas is to subsample, not take each one of the samples that you need to reconstruct the image. It's in the Fourier domain. I won't go into the physics of MRI machine. But if you subsampled and not take the entire measurements that you need, you will get low resolution, aliasing effects. So this is a classic task for deep learning. You input the low resolution images, and you're trying to predict high resolution images. And it's worked great. But like I said before, we try to think what we can do better. And what we suggest is to use the gradients not only to optimize the reconstruction model, but take them even further in order to optimize the acquisition process itself. In this case, in MRI, the acquisition is controlled by the acquisition trajectory, but it doesn't really matter. It's just some parameters of the MRI machines that we need to design. Usually, we do it by handcrafted trajectories, handcrafted heuristic in order to find the best acquisition parameter. But we suggest to optimize it, to learn and to find better data point. And if we will take better data point, it will be easier for us to reconstruct the image better. And truly, this is what we found. We can optimize the acquisition trajectory. You can see the learned trajectories on the bottom right. And they also perform much better in the end results. And also, interestingly, it's highly adaptive to the end tasks. For example, if we'll try to optimize acquisition parameters for segmentation or for reconstruction, we will get different trajectories because we need different data points to perform best in each one of these tasks. And also for different organs. For knee and brain, you can see the trajectories are very, very different. And this allows us to tailor our acquisition specifically for the task of interest. Similarly, we did a few follow-up works, one of them in a diffusion MRI. Very similar, the general idea is the same. Diffusion MRI is different MRI modalities which is sensitive to the diffusion of water molecules inside our body. One of the interesting use cases is tractography, where you're trying to create a map of the brain's fibers. But unfortunately, in order to do it in high resolution, you need to take multiple scans, multiple volumes, scan multiple volumes of the brain, each one of them sensitive to diffusion in different direction. So it's even slower, or limits the resolution even further. So again, we suggested a way to reduce the amount of volume we need to scan by optimize the acquisition parameter. In this case, the direction where you take the images, if you can say. Additionally, we show similar results also in different imaging modality, which is called the MIMO radar imaging, multiple input, multiple output radar. Also, it has many pros, but unfortunately, because of the high amount of received channels, it has high cost and high power demands and low frame rate. So we suggested using the same pipeline to learn the acquisition parameters, in this case, to reduce the amount of antennas and learn the antenna's location. And again, we show that you can learn better acquisition parameters and get better end performances. I won't go into the detail more than that. And now for molecule design, it sounds totally unrelated, right? But it is, we will see in a minute. So in molecular design, the task is to, given some properties that you want, to find the molecules that generate molecules that that have these properties. So let's say we have already a pre-trained properties predictor, which given a molecule as an input, give us the prediction of the properties. And we can calculate loss on that, right? According to the targets that we want to arrive in. And I guess you already know that I want to propagate the gradients even back to the input, but I don't really can change X, the molecule, because molecules are of a discrete nature. I can't move one atom, it won't be any valid molecule anymore. So we suggest to take it even further away and change the way we create the molecules. And for doing that, we used off-the-shelf guided diffusion model. In diffusion model, you input a noise, and each iteration, you clean it a little bit until you output a valid molecule. And we suggest also to inject in each one of these iterations, not only the denoising step, but also some gradient step. Again, the same gradient of the loss to the properties predictor. To inject it in each one of the iterations, we didn't just sort it by our own. It has a mathematical proof that shows that it's equivalent for sampling from the conditional distribution. And you can see that, for example, we had a data set of 500,000 molecules, and we looked on one specific properties, the UMU-LUMU gap. And this is the distribution of these properties in the data set. If you sample from unconditional diffusion model, you get very similar distribution. And as you increase the guidance scale, you can see that you can guide your distribution toward your desired targets, higher UMU-LUMU gap in this case. And even in one single batch of sampling from this generator, we can see that we can find new molecules with higher UMU-LUMU gaps than any one of the 500,000 molecules that we used during training. Okay, so for summary, same idea. Eventually, we can use the neural networks in additional ways. we can extract additional powers that coming from the gradients, and we can do much greater things and new things. Thank you.
Hi. Very interesting talk. Is there any issues with propagating the gradients when you model, in terms of optimization issues, when you model the sensor, not the neural network? Neural network is a lot of parameters, it converges somehow to some good optimization, but what about the sensor optimization?
Yeah, so eventually these forward models that we're trying to optimize, it must be differentiable. Like, it's not even need to be differentiable from end to end, it needs to be differentiable according to the parameters that you're trying to optimize. But yes, each time, and it's create a new difficulties, each time require different solution. Each one of these papers that I showed solve this issue differently. But yeah, it causes a lot of optimization issues, and we need to find different solution each time.